All right. All right. So we're gonna get started with the lab. So I just wanted to give you guys the correct answers. Okay. So with the first one, as an 8-bit number, which bit must be a 1 if a binary number a representing a negative value? Bit 0 refers to the least significant bit. Bit I is 1 for all 8-bit patterns representing negative values. What is I? Da 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 da. Okay. That's bit 7, not 8, 7. All right, moving on. Okay, so we have to check. So that would be the sign flag. Okay, think. Okay, to get the instruction we need to use, we first have to examine the ALU itself, which flag in the ALU reflects the sign bit of the result of a computation regardless of the computation, with the exception of the instructions decrement and increment. So there'll be the sign flag, which is S. Okay, moving on. Uh, Let us now shift our attention to some other instructions. Certain combinations of operands do not make much sense or do not do much with certain instructions. For example, AND AA does not really do any useful computation, and the same applies to OR AA. In a slightly different way, compare AA also does not do much. Regardless of the value of register A, what is the outcome of compare AA in terms of the resulting flags register? If you're not familiar with the layout of the flag register, you might want to review the ALU circuit and find out how the bits are arranged at the output pin flags out. Express your answer in a 5-digit binary number, such as 01101. Okay, so let's work with this one because I think this is the question, right? All right. So when you subtract a bit pattern from itself, okay, so that means we have x7, x6, x5, x4, x3, x2, x1 minus, guess what? The same thing. x7, x6, x5, x4, x3, x2, x1. Oh, forgot x0. There we go. Alrighty. Well, I think it is pretty easy to figure this one out, right? The Q is the exclusive OR, so they're going to be all zeros. All right. And then the borrow is also going to be all zero because the same bit minus itself will never trigger a borrow. So the borrow row or the T row is going to be all zeros with an extra zero as T8. Okay. So when you subtract zero from zero, guess what? You also get just all zeros. One, two, three, four, five, six. Okay. I need to pause the ones that are not working. There we go. All right. Right. So now you go like, okay, what about the carry flag? That's a zero. Okay. What about the Z flag? Well, the Z flag is the NOR of all of these zeros. So zero, NOR 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 zero is a one. So the Z flag is a one. The next one up is the sign flag. This is the sign flag. It is a zero. The next one up is the overflow flag. So in the subtraction, the overflow flag is um, making sure these two are the same and this one is different. Okay, but they're all zeros. Well, I shouldn't say they're all zeros, but these two are the same, which means the overflow has to be a zero. Okay, so overflow is a zero. And then the L flag is the exclusive OR between the sign and the overflow, which is now also guaranteed to be a zero. So the only one is the Z flag. The Z flag is bit 1, which means the answer is 0, 1, 0, 0, 0. Ah. But this is the ordering of the bits the way we have been talking about the entire time for the entire semester. Uh, okay, the answer to the previous question is why the opcodes of some combination of operands is quote unquote hijacked. Hijacked means a binary opcode is used for something else, blah, 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 blah. So in this case, TAC remembers that some operand combination opcode of either the AND XX or the OR XX families are hijacked for other instructions, analyze the opcode table and find out which family is actually hijacked. Oh, did you forget something? Oh, oh, okay. All right. That's all right. No problem. Hmm? All right. So instead of writing it, I'm going to run it in Logisim so you can actually see where you can find out how they are organized. So you go to all you need is really the ALU, but since I might need to run the processor anyway, so might as well just do the whole thing. So the whole thing is basically here. You can see how bit 0 is the carry, bit 1 is the Z, bit 2 is the sign, bit 3 is the overflow, and then bit 4 is the only one that does not quote unquote have a name. That's our L. No, no, we did not do it in the opposite order because bit zero is bit 0 is the one to all the way to the right hand side. Yep. So it's C Z S O L. You can try to come up with a acronym. LOZK. LOZK. Yep. Yep. Okay. All right. So where were we? Right here. Okay. So analyze the opcode table, find out which family is hijacked. Okay. So between those two, it is the OR that is hijacked. All right. Combining the result of the previous steps, we now have an efficient way to check whether register X, whatever X is representing, has a negative value by using the single bit of the flex register, which I do not name here because I don't want the later question to answer an earlier question. So let's call the mnemonic of the instruction that is not hijacked as test XX. It updates one of the bits of the flex register to indicate whether VSX8 is less than 8 or not, X referring to the register specified by X here. Note that the mnemonic test does not exist. It is just a placeholder, so the question of step 1 or one step does not answer the other one. Blah, 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 blah. Okay. So test XX is and then we have JYIL1, and then this is L1. Um, Obviously, JYI is yet another placeholder for a real mnemonic. What is the actual mnemonic to use in this context? It will be JSI. Yep, that is correct. JSI looks at the sign bit and only the sign bit. All right, number 6. Based on the previous steps, we can now write some code that can be assembled and tested. You might want to make sure that you answer all the previous parts correctly before proceeding with this one, because I see a lot of people just going like, I'm just going to try it. You know, and da 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 da. What definition of K1 caused this code to halt at halt 2? Okay, so halt 2 is here. Call this halt 2, right? This is halt 2. It is at label L1. Now, label L1 cannot be sequential to this halt because there's nothing after halt, okay? You get to the first halt, it cannot get to any additional code after that point. So the only way to get to label L1 is to go through the conditional branch instruction, which we have already identified as JSI, which means by this time the sign flag should be a 1. So, and then the previous instruction will set the sign flag according to the content of register A. So now the question is, which one of these will have the sign flag being a 1? Yep, 155, because it's greater than or equal to 128. There we go. Moving on. All right, at this point, you might want to write some code to assemble it and test it in the simulator to make sure the sequence of mnemonics from the previous step does work as expected. Blah 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 blah. Okay, how do we are now ready for the next step, which is the final step of this program. How do we perform arithmetic negation? Specifically, what is the name of the following C++ expression with respect to the bit pattern of x? It's 2's complement. Very good. And I think that's it. And then this is really just to go upload the program that you have written and so on. And that's it. Hmm? Yes. So test should be AND, A-N-D. And then JSI is JYI. That is correct. Yep. So that's the whole thing. It took me a little bit of time to figure out, how to make these labs, okay, because it has to illustrate the concepts and it has to present a little bit of a challenge, but not too much, right? So it was kind of fun, making all of this. And it's also even better when Canvas is up and running. Yep, that one. Ah, okay. I'm sorry. Alrighty, so we are now ready for the next topic because we have addressed how to handle control structure at this point. Basically, conditional statements, the two kinds of loops, how do we handle complex Boolean expressions, how do we reduce all of that to things that we can actually represent in assembly code. So now we are moving on to something that is a little bit different. I would say it is orthogonal to what we have already talked about. So you don't see this part here because I think that's for today's lecture. So we are moving on to calling and returning from a subroutine. Okay, so this is our next module. And it starts with an example of a C program that does absolutely nothing other than as an illustration of how call and return works in C++. So in this case, we have main. It calls f twice. F does not do a single thing, does not return any value, and then we are done. So the point is, okay, calling is pretty easy. Function f is called in main, so we continue execution in function f. F is going to return. So here's the first question. How does it know that it's supposed to return to the second function call of f? That's the first question. So whatever magic happens, it returns to the second function call, and then the second function call calls f again, f returns, but this time it has to return to the return statement. So that means where it has to go back to is not a fixed point. Okay. Yep. Yep. In a certain way, it is a label, but it is not a label. It's not static. Okay. The whole point is it is dynamic. Somehow, because if you use labels, there will be two labels involved, right? The first label would be here, and then the second label would be here. But so it has to know which one to use to go back to the caller. Okay, so you are partially correct that there are two labels involved. Okay, yep. All right, so in order to understand the whole thing, we have to use a quick digression to talk about the stack a little bit. So the stack is basically a data structure, or I should say a container that has LIFO or last in, first out as the way that it stores and retrieve items. Okay, so last in, first out simply means, okay, what do you get out of the container depending on how you put things into the container. Okay, so the best example of a LIFO or last in first out is a U-Haul truck, okay, especially a long one, okay. So whatever item, like usually a bicycle, okay, which is the last item that you try to push into the U-Haul truck before you slam the tailgate, will be the first item to fall out of the truck when you get to your destination. Is that right? Okay. So sometimes people make a mistake of putting the map to where they're supposed to go into Granny's Nuke, okay, which is the deepest portion of the U-Haul truck, and then they get into the driver's seat and go like, "Where's the map?" Yeah, that is painful. But that illustrates the order of last in, first out. Okay. Are we good with that concept? Last in, first out? Okay. So as it turns out, last in, first out is very, very important in computer science, not just in this class, okay? In computer science, last in, first out is a very, very important concept. In a certain way, it is more important than first in, first out, okay, which is a Q. All right. So the way we want to look at this is um, the concept of a stack is when you push something, you're storing something. So when you push 24, the stack has 24 in it. When you push 61, it is pushed to the top of the stack, which is the left-hand side of this notation. So when you push 11, then 11 becomes the leftmost item, 61 becomes the next item, and then the very first thing that you push is 24. So that means the tailgate is on this side. Okay, this is the tailgate of the U-Haul truck. When you pop, you are retrieving items, but in a stack, you can only retrieve the last item that you push, or whatever item is closest to the tailgate. So that means when the stack looks like this, when the U-Haul truck looks like this, the first item that you retrieve from the U-Haul truck would be the 11. And then the next item that you retrieve would be the 61 because the items are basically organized in that particular way inside the truck. And then if you try to push 5 again at that point, then 5 becomes the item that is right next to the tailgate. If you push 78, then 78 becomes the item that is closest to the tailgate, and then 5 becomes one level deeper into the truck. When you pop again, it retrieves the 78. If you push 100, then that becomes the latest item, blah blah blah, and so on. So this is basically just a sequence to show you the behavior of a truck. Do we have any questions about the general description of what is the stack, the way that we put items into the stack, and the way that we retrieve items from the stack? Okay, yep. So when the stack is empty, which is denoted by open and close square bracket, then it is a quote unquote illegal operation because you really do not have any items on the stack to retrieve. Yep. hmm You need to pop the third time you pop, you'll be popping the 24. That is correct. Yep. hmm Yes. So yes. So you can get to a value that is inside the truck, but you cannot retrieve it. So the retrieval order is always last in, first out. But you can say, okay, I want to get an X-ray to see if the TV is already packed in the truck. You can do that. You can kind of take a peek into the truck, but you cannot take it out of the truck. You can only go like, okay, can I take a look at what is in the middle section of the truck? Yeah, you can. You can use an X-ray machine to do it, but you cannot retrieve it. Okay. Alrighty. So another example that you can also use to kind of understand what a stack is your refrigerator, which is not intended to be a stack. It is much better off as a FIFO, but most of the time we use it as a stack. So that means the items that are kind of like further back in the refrigerator, they become a mode farm or mode garden with all kinds of colors because you never get to that. And then whatever, milk or cheese or whatever that is at the front, you consume that, you go like, oh, we need to buy new ones. But then you forget that, oh, we have another 2 packs of cheese behind the cabbage, which is already rotting, which is also behind, another, piece of pizza, which is not rotting because pizza can never rot. So you look at the pizza, it's like, oh, it is still fresh. I can still finish it later. Okay. Not aware that there are a whole lot of stuff that is rotting behind it. hmm So that's another thing you can remember is refrigerator, which is not really a good idea to use it as a stack, but most people use it as a stack. Alrighty. So now we get to the C++ implementation of a very simple stack. So we're going to start off with some definitions. Okay, so these are the definitions. I personally like just regular C without using C++. So the whole thing of using const is like, whatever. Okay. So I use pound define, which is a macro definition. All that really is saying is stack size, all in uppercase, is really just 32. Okay. Except in this case, it is a lexical kind of thing, which means the preprocessor of a C compiler basically just says, okay, fine, wherever I see stack size, I'll replace it with 32. That's basically what a macro is. Hmm? So it's not really a variable. It is called a macro definition, macro macro. So a macro definition is really just a text replacement method where in this simple case, the preprocessor of the C compiler would first go through the entire program and it would replace every occurrence of stack size with the definition, which is just 32. So it's a symbolic operation as opposed to a const in C++, because a const in C++ has a type associated with it. So it would do all kinds of type checking and whatnot. This one doesn't care. It is just really literally replacing stack size with 32. It doesn't even know what 32 it means. It's like 32, what does it mean? I don't care. Whenever we see stack size, replace it with 32. Nope, nope, nope. It does not do any conversion. Huh? Huh? So when the compiler sees stack size over here, it would just go like, okay, replace it with 32. That's all. Not at that point. When the compiler sees it, then it knows what it means. The C preprocessor is one step before the compiling. So the C preprocessor, its only job is to do text replacement. The C compiler, on the other hand, would look at the 32 and go like, okay, what do we do with this 32? Okay. Anyway, so the second line is declaring an array, okay, which is a unsigned integer 8-bit wide for each item, and we have 32 items. It's an array of 32 unsigned 8-bit integers. All right, and then the third line is a pointer, okay. SP is a pointer. It is a pointer to an unsigned 8-bit integer, and that's it. Yep, because stack size is 32. Yep. hmm I mean, I choose 32 just as an example, right? You can make it any length. Yep, that's right. All right. So now what we do is we now define the push operation. So using these three lines, which I think is going to be helpful if I were to take a snapshot of this and just kind of make it appear somewhere on the screen. Okay, so we'll do that. Because we're going to scroll off, that portion, so I kind of need to refer back to it from time to time. So I'm going to stick it up here. So the push operation would be these two operations. So let's assume that x, whatever x is representing the value that we want to quote unquote push on the stack. This is how we push, which is kind of awkward because most people say, don't you want to start from the beginning and move on to the next location? That is not how a stack works in computer architecture. So a stack goes from high location, and as you push items onto the stack pointer moves down to lower locations. Okay, so this is one thing you kind of have to remember because it is counterintuitive. So the way we do it is we decrement the stack pointer, and then we store whatever value we want to save on the stack to where the stack pointer is pointing to. Okay, the parentheses in this case are not required. It is simply a kind of exaggeration that we are using dereferencing. So the opposite, which is how you retrieve items, is exactly the opposite. Okay, we go to wherever the stack point is pointing to, retrieve the value at that location, put it into a variable x, which is supposed to store the retrieved value, and then we increment the stack pointer. So now the really important question is, then how are we supposed to initialize the stack pointer? Because if we initialize the stack pointer to be pointing to the beginning of the entire array, then it's not going to work because the first decrement is going to move the stack pointer to below the starting point of the entire array, so it's not going to work. So the way it works is this is how we initialize the stack pointer. It points to not the end of the array. It points just one byte past the end of the array. It is one above. The reason why it has to be like this is because the first decrement, when we push the very first item on the stack, I'm trying to adjust the scrolling to where I need it. There we go. So the first decrement is going to decrement the stack pointer to exactly the last location of the stack. Are we understanding this okay? Do you guys want me to kind of run this as an example in GDB? Okay, let's do that. Okay, all right, so what we'll do is we're going to use online GDB. Okay, so we will go ahead and take out this code, and then we'll do exactly what we have talked about. And then the first thing I need to do is to pound include standard integer.h so that the uint8 underscore t type def is available. So now we're going to do the rest. Okay, so I can put all of these as local variables inside main. So we have the first one is a pound define. I think the pound has to be on the leftmost side of a line. And then you can now say define stack size to be 32. So it's the same as what we have before. Okay. And the editor is trying to be smart. You're like, no, I do not want that. Don't try to be smart here. Um, right. Next thing is to define the stack itself. Uint 8 underscore t stack, and then we have stack size here, and then we have the stack pointer. So that would be uint 8 underscore t, asterisk sp for stack pointer. All right. So now we go for the initialization, which is sp equals to. So there are two ways to express this. My personal preference is to do stack plus stack size. Okay, but it really means the same thing as sp equals to the address of stack open square bracket stack size. So these two statements are identical in terms of their meaning. They are just syntactically different. We good so far? Okay, but you have to remember this is not a valid index into the stack array. Okay, this is one element past the end because we count from zero when we're indexing. All right. So now what we can do is to do some pushing and popping operation. So now we can do a push. Um, so a push would be, so I will also use macros, to implement the push operation, just so that I don't have to write all those lines over and over again. So a push operation, so you can now say define push, okay? And this is a placeholder, it is a parameter. So macros can be parameterized. So now this becomes basically the two statements that we were just talking about. First one is decrement the stack pointer, and then the second one is to say whatever the stack pointer is pointing to is going to store whatever x is containing. So that's basically a push operation. Now, if for those of you who go like, Tech, I think we can combine two statements into one. The answer is, yeah, we can, because we can pre-decrement the stack pointer before we dereference it, which means this is exactly the same thing as not having the pre-decrement over here, but instead pre-decrement SP before we dereference. It would mean exactly the same thing. Okay, but most people do not like to read it like this because they really want the order of operation to be well spelled out. So this is why this is the preferred way of doing this, but it's not the only way to do it. Are we doing okay so far? Sorry? Yep. Exactly. Eye candy. All right. So this is a push, and then the pop is going to be kind of the opposite. So in this case, the pop operation, I'm not even going to give it a parameter because what we'll do is we're just going to use a printf statement to print it out. Okay, print out whatever value that we are retrieving. So we know those are 8-bit integers. So I think we can use a percent %u, and then we have to do some casting. So we say pop this, okay? And then the other side would now have to specify what we are popping. So this time I don't have an option. I have to combine the post increment inside the same expression because I'm now at a place where I can only specify um, an expression. I could do it the other way too, I suppose. Okay, so we have to do a unsigned type casting because whatever the stack point is pointing to is not a regular unsigned, it is an 8-bit unsigned. So I have to cast it to a regular unsigned because that's what the percent %u is expecting in the format string. So now we can do this. So it will print out whatever we are retrieving. And then after that point, we also have to increment the stack pointer. But once again, you can combine the operation. So instead of having the SP++ like that, you can also put the SP++ inside the parentheses so that you are using post increment inside the dereference. So that works exactly the same way. Yes. Mm, on which one? On the pop or the push? So the two, okay, so the minus minus SP is allocating a space for the next item to be stored. So you have to allocate first before you put an item to the space that you just allocated. But when we're deallocating, yeah, so the plus plus is for deallocating that space. Yep. All right. So with these two macros defined, and we have the stack pointer initialized. So now we can just use the macro like push 652 uh, push 100, pop, and then push again. Let's push 32 this time, and then we do pop pop. Okay, so that should get the stack back to the empty state and return 0. Okay, so according to this, the program should print 100 for the first pop. It should print 32 for the second pop, and it should print 52 for the third pop. Is that okay? So we'll go ahead and try this out. I need one more pound include for printf, okay, standard io.h. So this is how people write code before C++. This is straight up C, not C++, um, which is what I prefer to use for this class. So we'll go ahead and we can just run the code, okay, because it actually has side effects. And why is it not running? Hmm? Oh, choose language. That's it. C. There we go. So it basically pop 100, pop 32, and pop 52, the same way that we described it. So if you guys want to, kind of repeat this experiment, you can just kind of write your own um, and give it some try. We good? But are we understanding the concept of pushing and popping? All right, cool. All right, so now we can get back to the note here, okay? So the question is, why do we need to talk about the stack? The answer is this is where we save the location of where a function is supposed to return to when it's done. We are using the stack as a way for the caller and the callee, the function being called, to communicate with each other. Okay, so the stack is very central in every C program, every C and C++ program. The stack is a very important feature. Has anyone heard about what is multi-threading? Okay, so the key of multi-threading is each thread has its own stack. Okay, that's multi-threading, which is not the same as multi-process. Okay, so a process can have multiple stacks, one stack for each thread. But the processes, if you have two processes, they do not share the same memory space, so they cannot refer to variables of each other. But when you have multi-threading, they can, in fact, refer to memory locations that are shared. So if you use the heap for dynamic memory allocation, or if you use global variables, then a multi-threading program can use the global variables to communicate with each other. Fun stuff. Okay. Yep. Yes. So static is the same thing as a global variable. So the only difference between a static local variable and a global variable is the scope. But the lifespan is exactly the same. They are both at a static location. It's just that certain parts of a C program has visibility to that location, and most other parts do not when it is a static local variable, as opposed to a global variable, which means everything in the same file knows where to find that global variable. But then you also have super global, or I take it back, sorry, I take it back. You can have you can have global variables that are only local to a file. And then you can have global variables that are global across multiple source files. Yeah, so there are ways to indicate this is a global variable, but we want the visibility to only to be in the same file, as opposed to the linker has visibility to it. I believe the keyword to make that happen is static itself. All right, so getting back to this. So now the question is, how do we implement this program? How do we call and how do we return? So instead of talking about these individual pieces, I'm going to talk about the entire thing. I will write the program as a whole, but not in the order of the actual code. Okay, so I'm going to jump around a little bit to explain the various parts. All right, so let's go ahead and go to my editor. I think this works. Okay. And just have to kind of bring it here, increase the font size a little bit. I think that's good. That is good. All right. So now we go back to the temp folder. Actually, I can put it somewhere else, but it's okay. All right. So I just call this a call return.ttp-asm. And then the first thing I'm going to do is to kind of repeat the C program, but only as comments. So this way, we can actually identify which part of this program is implementing which part of the C program. So there we go. We have main. It calls F the first time, then it calls F the second time, and then main itself returns 0, and then that's the end of main itself. Okay. So first thing first, okay, every function, including main itself, is really just a label that has the same name as the function itself. Okay, because the label main in this case is identifying, okay, where does main start? Okay, that's what the label is for. So with calling f, okay, we know that one step of calling f, so f is the same way, right? F is going to have a label f to identify the entry point of function f. Okay, now that's not the entire function f. I'm just writing the program in a very quote unquote scattered mode, because I'm trying to explain concepts and will fill in the program as the concepts are explained. So we know that one of the steps of calling function f is going to be just jmpf, which means we are just continuing execution from where main is to where f is starting. Okay. The problem is we have to somehow get the program to remember where it is supposed to go back to. So we have two JMPI to Fs, but then the F function, it has to go back to the correct spot, right? So the only way to do that, okay, I'm going to use comment here. So the first thing we need to do is to push the return address first. And then what we need to do here is to pop the return address. The return address is simply where in the caller should we continue to execute when the function is done. So are we okay with that term? What is a return address? Okay, it is the address of the caller where execution should resume when the function being called is done. So we good with that concept? Okay, all right. So now, where is the return address of the first call? Well, it's actually here. Okay, so we can call this label return address 1, which is the return address of the first call. It is right after the JMPI, the JMPF, the JMPI to F. Because if I move the label one line earlier, then we'll be going back to the same location where the JMPIF is. So now it would just keep doing the same thing over and over again. That would not be the right spot to do it. And then for the second call, the return address is going to be here. So return address 2 is going to be here. Are we good so far? Yes? Okay. So now we go like, okay, since we are supposed to push the return address 1 over here, and we're supposed to push the return address 2 over here, so now the question is, how do we do that? Okay, because we know how to do this in C. Okay, we know what this is really doing is saying, okay, we need to decrement the stack pointer, and then we store the return address to whatever the stack pointer is pointing to. Is that okay? And then for the second one, kind of the same thing, except it is dealing with return address 2. And then when we are over here, we're popping the return address into a register. So we go like, okay, pick a register. Okay, we'll pick register C. Okay, so we're going to say, oh, register C is going to be um, whatever the stack pointer is, because that's the first operation of a pop operation. And then after that, we are going to increment the stack pointer because we are reclaiming that location. Are we doing okay so far? So these are the same things that we saw earlier in the C code. We don't know quite how to do it in assembly code yet because the biggest question is who is the stack pointer? Okay, but now we are basically getting like, okay, I think this is going to we need one more thing, okay, which is a special jump instruction, and then somehow, okay, continue execution at the location where C is pointing to. Okay, okay. So the comments is already telling us what we need to do, but it doesn't quite tell us how to do it in assembly language. But the first question, so we need to first understand the comments, which is abstractly what we need to do before we actually learn how to do it. Do we have any questions at this point? Go ahead. Mm-hmm. Mm-hmm. It depends on how we got to F. It just really just retrieves whatever is on the stack. So it depends on how you got to F. Did you get to F because of this JMPI, the JMPIF? If so, then you are popping return address 1. Or did you get to the same spot because of the JMPIF on line 17, in which case you are retrieving return address 2? But that's a very good question. I like that question because your question answers or illustrates exactly how a function knows where to go back to because the caller sets up the whole thing to begin with. Is that okay? In this program, yes. In this program, that is the case. So, okay, so now we look at this and go like, okay, so the whole thing has to do with who is the stack pointer because we don't see a stack pointer as a register. There are no registers with the name of SP. So we go back to the notes. Okay, the note says we are just going to use register D as our stack pointer. So at some point, somewhere, it is going to say that. I cannot remember where it says it. Uh, Cannot believe it. I cannot. It doesn't. It doesn't say it because it's another piece of notes. Okay, so let me keep this one here when I look at another one. It is called the most important document for all of you is the caller callee agreement, which is here. There we go. So this is a very concise document in a way. Okay, but it is basically saying the stack operation specification. We are using register D as the stack pointer. So from here on, in this entire semester, from here on, register D is now special. Okay, its only job in life is to serve as a stack pointer. Every time we refer to the stack pointer, it is register D. Now, is register D actually special in the processor that makes it the special, stack pointer? The answer is no. So when we go back to Logisim and then we go to the register bank, okay, and then we look at register D, we go like, does it have any special connection to places where the other registers cannot go? The answer is no. The only way for register D to output its content is to go through the very same multiplexers as every other register. So that means the stack pointer being register D is a convention. It is not designed into the hardware. Registers A, B, C, and D, they are all what we call general purpose registers. None of them is special. Is that okay? So when I use those terms, okay, registers A to D inside the register bank are all general purpose registers. They are not special purpose registers. That implies in some other architecture, the stack pointer is actually special, along with some of the other registers. So those architectures make use of special registers or special purpose registers. The TTP text toy processor does not make any differentiation across all the registers. It is only a matter of how we use the registers. It is not baked into the architecture itself. Is that okay? Because that's a very important point for us to remember. All right, so getting back to the code, which is here. So now that we know the stack pointer is really just register D, so that means, oh, okay, everywhere we see SP, we just replace it with a D. Okay, like that. And then we have that, like so. Okay, so now we look at each one of these operations and we go like, do we know how to do that? Okay, we'll start with this one. How do we decrease one in register D? DEC, decrement, okay, decrement D, okay. And then the second one is how do we store the value of return address 1 into not register D, but where it points to? So this is where I'm gonna give you guys a few alternatives that are all wrong. Because it's important to know what is wrong, why they're wrong before we introduce the correct answer. Okay, so we go like, okay, I vaguely remember LDI instruction, something like this. Okay, all right, yes, this is a legitimate operation, except it doesn't do what we want it to do. Because this one, unfortunately, is only doing this. That's what it does, which is not what we want to do. Okay, can someone tell me what is the difference between line 11 and versus line 13? Just focusing on the assignment operation. Exactly. Okay, so both of you are correct. You use the term dereference, and then you use the term of where it's pointing to. They both are exactly the same thing. Very good. So that means, okay, it doesn't quite do what we want it to do, But I vaguely remember in ST and LD, the parentheses means, indirect, okay, or using the register to point to whatever location. So maybe we can do it like this, okay? Just put parentheses around D. No, the assembler does not like it, okay? It does not like it, not because the syntax does not allow it. The syntax, once again, is just eye candy to show you what you can and cannot do. The reason why we cannot do it is because the architecture does not have pathways to do it. The architecture has no pathway to retrieve the immediate value and then immediately, or using some following steps, to put it into some place where the register is pointing to. Okay. Now, can I implement an opcode to do something like that? The answer is maybe. Okay, maybe. Um, but it doesn't have it. Okay. So that means, oh, okay, this doesn't work. Darn it. Okay, fine. What about the LD instruction? The LD instruction does not work either because the LD instruction says, okay, we are going to a location to retrieve the item. So that's not the right one to use. What about ST? So ST means, ST has a destination that is indirect, but it needs a register as the second operand. So that doesn't work either. So the only way to solve this problem is to quote unquote burn one of the other registers. Let's say register A. So we'll do LDI register A with return address 1. Then we can use ST with register A. So it has to be broken up into two parts because of the limitations of the instruction set. Is that okay? All right. So that means this is going to be about the same thing. Okay, decrement D, and then we have a LDI register A. Okay, whatever register you can use whatever register you want. Okay, ADDR2, and then we STDA. Okay, so just to emphasize that we could have used any register, I'm just going to stick with register B over here, and then stick with register A over here. It doesn't matter which register you use because the ultimate goal is to store that into the stack. Okay, register A versus register B is just a vehicle to put it into the stack. Yes, ST is store. Okay, so ST, so this is where the RTI really comes in handy because the RTI tells you how an instruction gets the job done. So when we go to the opcode table and then we go to the ST instruction, this is the ST instruction. You can see what it looks like, right? Okay, let me just copy and paste it here. Okay, okay, okay. That's a tiny little one, but it is still useful. Do you see how ah, there's not enough place? Oh, I can grab it. There we go. Do you see how this is related to this? The only thing we cannot do is I cannot specify a constant over here. X has to be a register. So that's why I have to go through, in this case, register B, in this case, register A, in order to finish that operation. Is that okay? All right. So now we can close this. All right. So I think from the caller's perspective, we're all done. Well, I mean, almost all done, but we'll just call it done for now. And now we go to the callee perspective, okay? So can someone tell me what instruction would do this? We're trying to retrieve whatever is at the location that register D is pointing to, and then store that into register C. What instruction can be used in that case? LD, yep. It'll be LD D, okay? So the order, so when you have two operands, one is going to be changed. The one that is going to be changed is always the one on the left-hand side, because I want to maintain um, the left-hand side versus right-hand side ordering of an assignment statement. Okay, because when an assignment statement, the right-hand side supplies the value, the left-hand side stores the value. All right, so that takes care of that. What about the plus plus D? What do we do about the plus plus D? Increment D. Okay, very good. So now we are now going to this mysterious part, which is somehow continue execution at the location where C is pointing to. Okay, that sounds like somehow we want the program counter to be changed by just C. Does that sound right to you? Because the program counter points to the next location that where we're going to fetch the next opcode. So if I can just change the program counter directly to where register C is pointing to, then we're all good. Okay. So people might think, oh, okay, then we need a CPR PCC. Well, except it doesn't exist. Okay. Hmm? Because PC is not one of the four registers in the register bank. So now we go like, tag, did you actually make the architecture flexible enough to allow something like this to happen? So now we want to look at this up in column C of the opcode table. In other words, we're trying to look up the RTL description of our instructions to see if something looks like this, right? So now we go back to the opcode table with a focus on column C. It's right here. It's the second row, which is row 25 here. PC equals to whatever X turns out to be. And the mnemonic is JMP, whatever register you want to use. Oh, okay. So that means this is really just JMP without the IC. Okay. It's important to specify without the I, okay, because it's not immediate. We're not specifying a constant where we always go like, okay, go to that location. Okay, go to this static location. We are saying whatever is in register C at this point, go there. Are we good so far so with this code? Okay, so we only have to dress it up just a little bit more before we can run it. So the first thing we have to dress it up with is a no op because the very first operation has to be a no op if you want to use River Spider to run it kind of to run it in a convenient way. And then the second one is if I don't do anything, function F is going to be the first uh, code to run, which is oh the stack is not even set up yet. What are we going to do here? So we need to do a JMPI to main in order to change the direction all the way to main first. So now it's going to do all of these operations. When it's all done, I think it's good to have a halt instruction here, just so that the whole program stops, right? Hmm? It depends on the architecture. So in some architecture, they do have a return instruction, which is doing what these two instructions are doing. So in TTP, these two instructions together is doing a return. In many other architectures, there's a specific instruction. I take it back. I was wrong. I should be saying these three instructions. So these three instructions in TTP is performing a return. Okay. In many architectures, especially Cisp architectures, it is a single instruction. But even in many RISC architectures, it is still a single instruction because it saves a lot of code space. So you might be asking, but Tech, why are you doing this? Why are you not implementing the return statement or return instruction? Because I need you to understand what is under the hood of a return statement or return instruction. That's exactly what is going on under the hood. Okay, this class is about it's about explaining things that are under the hood and not so much how fast the car can go. Okay, so that's a very good question. All right, so I think we are ready to run this program. And the way I'm going to run it is to go through River Spider, just because it is the best way to illustrate and also visually show you what is going on the stack. Okay, so that's how we're going to do it. So we're going to push directory to the folder where the tool is located. There we go. And the whole point of River Spider is because the project originally was supposed to do something entirely different, and then they gave up on that project, and then later on found out that some portions of that code can be used for this purpose. So yeah, so it's a long history. It's hmm? Hmm. Yes, this entire thing is very homebrew. Yep. Um, huh? Well, I mean, this is the only way I know how to demonstrate every single component of what I want to explain. All right, so we're gonna use this tool, go through the whole assembly, run, trace analysis. Oh, okay, crap. It does not assemble properly. Okay, that's fine, but this is good. I like it when problems happen. You cannot imagine how often I tell my class, it's like, oh man, the program works the first time. All right, so why is it not working? Alrighty, I don't see any error messages here. Okay, RAM file does have something in it. The source file did not assemble correctly. Am I using the wrong? Ooh, no, no. Okay, let me double check, make sure the source is the one that we are dealing with. Okay, JMBI to main, F, LDI CD, increment D, JMPC. And then in main, we have decrement D, LDIB with return address 1, store, JMPIF. I don't see any error messages, and the RAM file is okay too. So why is it complaining? Hmm. Assemble tab. Okay. Looks clean. Everything looks clean here. All right. Well, it could be a glitch, even though I really suspect it's not, but we'll give it a try. It was a glitch. It was a glitch. This is, I don't know what to say other than saying, Google, you messed up. I don't know. I don't know. It's, yeah, this really should not have happened. Anyway, it did happen. Hmm? Yep. All right, so we go to the analysis tab. This is where the good stuff is, okay? So if you're signed in already, you can take a snapshot of this. Just go to File, go to, don't do download, it doesn't do much good. Make a copy, okay? If you make a copy of this spreadsheet right now, then you can annotate it any way you want. So anyway, right now we just kind of keep track of the program. Location 00 is a no op, doesn't do anything useful. And then we go to JMPI to main, and now we are in main. We do the decrement. You can see how D went from 00 to FF. So I did not initialize the stack pointer in this case, even though I'm supposed to. But the stack pointer already has a value of 00, which is one location past the end of the entire RAM. The last location of RAM is what? FF, 255. What happens when you add 1 to 255? You get 0 because we only have 8 bits. Okay, adding a 0 to 11111111 gives you 00000000. Okay, so in terms of modulo congruent, we are basically saying 0 and 256 are modulo congruent modulo 256. They are the same, they have the same representation, even though they are quote unquote two different values. So the stack pointer is now at FF, which points to the highest possible location in RAM. And then we load B with the first return address. So B is getting 0C. So now we're curious, okay? We want to say, are we really sure that location 0C is where the first call of F should return to? So we go to the assemble tab and then we look it up, okay? We look up the first call of F, which is down here. This is the first call of F in commands. So when it returns, it should return to return address 1. And then the next instruction is indeed at location 0C. So 0C is the correct return address to push on the stack. So now we go back to the analysis tab and we go like, okay, the next instruction is a stdb, which is, oh, it's doing exactly what it's supposed to. location FF is overwritten by the value of 0C. This is C syntax, okay, without the correct type checking and whatnot. But the asterisk here is intentional because it is indeed dereference. We are dereferencing FF and store the value of 0C to the location at FF. All right. So now what do we do? It has a JMPIF. So now you can also see the program counter went from 0A to 0C. So when you go to the assemble tab, you can see exactly what 0A is, which is here. 03 is over here, which is the first instruction of function F. Okay, so now we go back to the analysis a little bit more. The next instruction is retrieving the return address from the stack. So it is copying whatever the stack point is pointing to. This is the stack pointer. It points to location FF. So it retrieves whatever that location has. And then, so this is basically telling you that location FF has the value of 0C. So some people might be saying, I don't see how these two are different. They are different. This is an assignment operation with a single equal. This is a double equal, emphasizing that location FF has the content of 0C. So we are retrieving. And that 0C is now copied to register C. So at this point, register C has the value of 0C, which is the return address. And then we increment the stack pointer. The stack pointer was FF. Now it is 0, 0. And then we do a JMP C, which is using whatever value is in C and use that to overwrite the program counter. And as a result of that, we continue execution at exactly the location of 0C, which is in the caller in main. So in main, we're going to do about the same thing again. This time we used another return address, which is 1, 2. We push it on the stack. We get to the function, okay? And then in the function, we return right away, which means we retrieve the 1, 2 into register C, and then we increment the stack pointer to deallocate that location in the stack, and then we continue execution based on whatever register C has. So we continue execution at location 12, which is where the halt instruction is located, and that concludes the execution of the program. So are we good so far in terms of how a function is called and how it returns in assembly language? All right. So does that also help explain the importance of the stack in a C++ program? Okay. All right. So now is a good time to emphasize the importance of this particular uh, agreement here, because the agreement specifies everything that the caller and the callee need to know in order to communicate with each other. So the first thing is the stack operation, which is a repeat of what we have already talked about a little bit earlier. But then they also talk about, the mutual agreement. On the caller side, if there are arguments, blah, blah, blah. And then since we haven't really talked about arguments and parameters, for now, you can ignore this. You can just go like, there are no arguments. Okay, that F does not have arguments. It does not have any return value. But the argument does specify what to do with the return address. And then this is from the caller side, and this is from the callee side. So from the callee side, we do all the same stuff here. Since we have not really talked about parameters, you can ignore this. But we still have the return address. So this part is still relevant. The stack pointer still points to the return address at the entry point of the function. We haven't really talked about local variables, right? So we can ignore the local variable discussion, at least for now. Okay, so but the picture of the stack is here. You can ignore everything that has to do with parameters. You can ignore everything that has to do with local variables, but the focus is the return address. Okay, and over time, okay, we are going to go through this a lot more to talk about how local variables play get into the whole picture. We will talk about how parameters get into the whole picture, and we'll also talk about the return value, which is actually one of the easiest thing to do is the return value. So this is kind of the setup of this class. Today is really just the entry point to understand, you know, what is a call, what is a return, how it is done, what is the stack, what is the purpose of register D, which is the stack pointer, and how do we push a return address on the stack, how do we pop the return address from the stack. So that's the focus of today's lecture. Do we have any questions about this? Hmm? Yes. Parameters are pushed on the stack. Local variables are on the stack. But yep, well that's basically how C is doing things. And you also have to remember C is really a shorthand for writing assembly code back in the days when they were trying to implement the Unix operating system. So this is basically as low level as it gets when it comes to the understanding of those quote unquote higher level concepts of calling and returning. Yeah, go ahead. Hmm? Templates? You mean in C++? So templates is a form of preprocessor in the good old days on top of C++. So when you use a template, it is expanding the text representation of your template class to use name mangling to create functions that or classes and also methods that you do not know about. Templates is a very it is a kludge to solve a problem that C++ did not originally solve, and the kludge came in the form of another preprocessor to textually manipulate um, a source code that has template or the use of template into C++ code that does not have template. And then the names of the classes and the name of the methods are mangled because they are based on the actual name that you want to use, but then they also integrate the template name and also the parameters of the template as a part of the name of the functions and the class. So it's really kind of yeah, it is another hot mess. Hmm? Yes. So okay. So if you don't believe me, you can look up C++ template, and then you can look up name mangling. Is a mechanism used by compilers to create unique, unambiguous names for template instantiations and specializations, ensuring the linker can correctly identify and resolve symbols. This process is necessary because multiple template instantiations can share the same source level name but have different underlying types or non-type template arguments. Blah, 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 blah. It is a really hot mess. Okay, that. Hmm? Yes. So, yeah, so name mangling is a real thing. Okay, it may not be true anymore because I think modern day C++ compilers can handle all of that without an actual external tool to do all the name mangling. Just like this preprocessor. Well, the preprocessor is still a thing. Okay, it's called CPP. So on the Unix command line, you can actually type CPP. It is not C++, it is C preprocessor. So it can actually, okay, this is actually not a bad thing to illustrate since we got a little bit of time. So we can call this, test CPP. We'll just call it text file, okay, because that's all we need. Pound define stack size to be 32, and then we just say stack size plus 2, and so on. So this is just a regular text file. There's no C code in it. And now you can do a CPP, redirect from testcpp.txt. This is the output. So the output has a bunch of pound stuff. This is basically intermediate output so that the debugger can understand which line what got defined and expanded to what else. But the actual output of the code has the stack size replaced by 32. So if you ignore all the lines starting with a pound, the actual program is like that. So let me just kind of cat test cpp.txt. So you can see how 32 is stack size, and the 32 plus 2 is stack size plus 2. And that's what the CPP program does. All it does is to understand the macro definition. Um, the macro definition can get really hairy too because there are conditional stuff you can do with macros using the pound if. So you can really kind of get super complicated into the macro definitions. Pound include is also handled by the C preprocessor. So the best way to illustrate that is simply to do a CPP, which means now it's interpreting what I'm typing to be the input stream. So now I can say pound include stdio.h, press the enter key, and then press Control D so that we can stop the file. This is what it does. It actually goes to wherever standard input output is and then just substitute it in place. The pound with a line number here is so that we can tell the line number inside the um, this is the actual line number, but at the same time, it is also reflecting exactly where in the original code the pound include is, so that the debugger can still find the right place when there's a problem. Yes, so the entire tool chain used to be a big hot mess of individual smaller tools, where each smaller tool knows how to communicate with the next tool. Yep, yep. That's the history of C++ based tools. It is all over the place because the programming language was invented in the 70s. So since that time, it has been changed and modified a lot. Initially, it does not do a whole lot of type checking. Pointers are just pointers. Okay, it doesn't really care what it points to. And then later on, they added type checking, and then later on, they added the concept of a const, C-O-N-S-T, so that the compiler can say, "Hey, you're not supposed to change that," or "You cannot change that unless you typecast it." So you can still cast your way out of anything. All the safety features, you can say, I know what I'm doing, just let me do it. Yep, that's C++. Can't do that with Java. Java will not let you do things that you're not supposed to, regardless of how much you try to convince it. C++ is like, okay, I see you think you know what you're doing. I'll let you do it. Yep, yep. So I'm going to let you guys do the lab now. So the lab is called the stack operations. You cannot see it yet. You'll just give me a moment to set it up. Oh, this one you only have 3 attempts because I think in one of the semesters I was noticing people were just using the infinite monkey approach. I go like, no, that is not going to be helpful. So this one you only have 3 attempts. So be careful about those attempts. And then we'll change this date to October 22nd, and it would be 1:20 p.m. for this class. The access code is LIFO, all lowercase. So make sure it is LIFO, all lowercase. And I'll give you guys the whole lab period, of course. So it's October 22nd, due at 1:20 p.m. There we go. And then save and publish. There we go. So you should have access to it now. I'm just going to do a preview to see if there are any. Yeah, yep, that is the one. And I believe this one has nothing to turn in, so that you don't have any code to turn in like the absolute value one. You know, I skipped one. I skipped the compiling C control structures. So I take it back, unless you guys want to do two labs on the same day, because I think we should go for this one first. This one only uses the material from the previous class, so we're gonna use this one. I apologize. I forgot about this one altogether. October 22nd at 1:20 p.m. The access code is GCC on this one. Okay, so forget about the other one. I'm not gonna release it. I'll take it back. So GCC is the one, and change the due date. October 22nd, 1:20 p.m. Like so. Okay, so I'm gonna unpublish the other one, and this is the current one. This one does not have a limitation of how many times you can submit. Yep, compiling C control structures. So I'm gonna recall that one. The other one, which is stack operations, I'm gonna uncheck it, but it won't let me do it because some people have already started it. It's okay. I'll figure it out. I'll figure out how to do this. Hmm. All right. All right. I'll be back in. Oh, forgot to turn off my record.